there is a ghost in the machine. Not the machine of our technology, but the machine of the universe itself. And it's not just one ghost, there are trillions of them. In fact, right now, as you read the sentence, hundreds of billions of them are passing through your body. They are streaming through your hand, your screen, the chair you're sitting on, and the very planet beneath you. They came from the sun, from distant exploding stars, and from the beginning of time. They are passing through solid lead as if it were empty space, and you don't feel a thing. These are neutrinos, and they are called the ghost particles of the universe for a very good reason. They are everywhere, yet they are almost nowhere. They exist, but they barely interact with anything. They are the ultimate cosmic wanderers, the silent messengers carrying secrets from the most violent and remote corners of existence. To understand the neutrino is to understand why the universe is so much stranger and more subtle than it appears. Our story begins not in the far reaches of space, but in the minds of physicists in the early 20th century. They were feeling pretty good about themselves. They had figured out atoms, they had Einstein's relativity, and they were starting to understand the quantum world. But there was a problem, a crack in their perfect understanding of reality. The problem was a process called beta decay. Beta decay is a type of radioactivity. It's what happens when an atom has an unstable nucleus. Sometimes a neutron inside that nucleus decides to change. It turns into a proton. To keep the electrical charges balanced, it also spits out an electron. So a neutron becomes a proton and an electron. This seems straightforward enough. Physicists could measure the energy of the neutron before the decay, and they could measure the energy of the proton and electron after. Here's the problem. The most sacred law in physics is the conservation of energy. The energy cannot be created or destroyed. It can only change form. So the total energy you start with must equal the total energy you end with. But in beta decay, it didn't. When physicists added up the energy of the new proton and the new electron, it was always less than the energy of the original neutron. Some energy was simply missing. It had vanished. This was a catastrophe. It was like putting $10 in a sealed box, shaking it, and opening it to find only 8. Where did the other $2 go? For physics, this was a crisis. Some famous scientists, including the great Niels Bohr, were ready to throw in the towel. They suggested that maybe, just maybe, at the tiny subatomic level, the law of energy conservation was sometimes broken. It was a radical, desperate idea. It meant the universe wasn't as orderly as we thought. But another physicist, an Austrian named Wolfgang Pauli, thought this was a terrible solution. He believed the laws of physics were elegant and unbreakable. Giving up on energy conservation was too sloppy. In 1930, he proposed a different idea. He called it a desperate remedy. He wrote a famous letter to his colleagues, which he started by addressing them as "Dear radioactive ladies and gentlemen." He was too shy to present the idea in person, so he sent the letter instead. His idea was this: the energy isn't missing. It's being carried away by a third particle, a particle that nobody had ever seen, a particle that our detectors couldn't pick up. To explain the missing energy, this new particle had to have some very specific properties. It couldn't have any electric charge, otherwise we would have seen it. It had to be incredibly light, maybe even massless. And most importantly, it had to interact with other matter so weakly that it could fly through almost anything without leaving a trace. It was, in essence, a ghost. Pauli himself was not happy about this. He famously said, "I have done a terrible thing. I have postulated a particle that cannot be detected." It felt like cheating. It was like explaining the missing $2 by saying a tiny, invisible, silent thief was in the box. It was a convenient fiction to save a beloved theory, but the idea was out there. A few years later, the brilliant Italian physicist Enrico Fermi took Pauli's idea seriously. He developed a full mathematical theory around it, and he gave the ghost a name. In Italian, the neutron is the neutron, meaning the big neutral one. Fermi called Pauli's little particle the neutrino, which means little neutral one. The name stuck. Fermi's theory was beautiful. It perfectly described how beta decay worked, assuming this little ghost particle was real. But the central problem remained. How do you prove something exists if you can't see it? How do you catch a ghost? The challenge was immense. Fermi calculated just how weakly the neutrino interacted with matter. The numbers were staggering. To have a 50-50 chance of stopping a typical neutrino, you would need a wall of solid lead that was a light year thick. A light year is the distance light travels in a year, about 6 trillion miles. Our entire planet is a mere speed bump to a neutrino. This is the heart of its ghostly nature. Normal matter, the stuff we're made of, is mostly empty space. But the electrons and nuclei in our atoms have electric fields that get in the way of other particles. It's like a crowded room. Even if it's mostly empty air, you can't just walk through it without bumping into people. But the neutrino has no charge. It's like a person with no social presence at all. It can glide through the crowd without anyone ever noticing it's there. For more than 20 years, the neutrino remained a theoretical ghost. A clever idea, but just an idea. Then, in the 1950s, two American physicists, Clyde Cowan and Frederick Reines, decided to go ghost hunting. They knew they couldn't build a lead wall a light year thick, so they needed a different approach. Now, they needed two things: an incredibly intense source of neutrinos and a very, very big detector. For the source, they found the perfect thing: a nuclear reactor. A reactor during its operation is a massive factory for beta decay. It churns out a mind-boggling number of neutrinos every second, something like 10 trillion of them. It was the most powerful neutrino beam on the planet. For the detector, they designed a clever experiment they called Project Poltergeist. They built a large tank filled with hundreds of gallons of water. But it wasn't just water. They dissolved a cadmium compound in it. The idea was to catch a specific, very rare interaction. According to Fermi's theory, a neutrino, or more accurately, its antimatter cousin, the antineutrino, which is what reactors produce, could occasionally hit a proton. When this happened, the proton would turn into a neutron, and the antineutrino would turn into a particle called a positron, which is like an electron with a positive charge. This positron would immediately find an electron in the water. When matter and antimatter meet, they annihilate each other in a flash of light. So, the first sign of a neutrino interaction would be a tiny, brief burst of light. The detector was lined with light sensors to pick this up, but that wasn't enough. Other random cosmic rays could create similar flashes. They needed a smoking gun. This is where the cadmium came in. The new neutron created by the neutrino would bounce around in the water for a few millionths of a second. Eventually, it would be absorbed by a cadmium nucleus. When cadmium absorbs a neutron, it gets excited and releases its own distinct flash of light. So, the signature of a neutrino was a delayed coincidence. A flash of light from the positron-electron annihilation, followed a few microseconds later by another flash of light from the neutron-cadmium capture. Two flashes, perfectly timed, in a specific order. That was the ghost's fingerprint. In 1956, after years of painstaking work at the Savannah River nuclear plant, they found it. They were seeing the two flashes, the telltale signature, a few times per hour. It was unmistakable. They sent a telegram to Wolfgang Pauli. He was at a conference in Zurich. When he received the news, he and his colleagues celebrated with a case of champagne. His desperate remedy, his undetectable particle, was real. The ghost had been caught. Reines would later win the Nobel Prize for this discovery. The hunt was over, or so they thought. Science is never that simple. The discovery of the neutrino wasn't the end of the story. It was the beginning of a much deeper, stranger one. In the years that followed, physicists discovered other particles. They found a particle that was exactly like the electron, but about 200 times heavier. They called it the muon. And just like the electron, the muon was involved in its own particle reactions. And those reactions also seem to have missing energy. Physicists guessed that there must be another kind of neutrino, a muon neutrino, that was different from the electron neutrino involved in beta decay. And experiments later confirmed this. They created beams of muon neutrinos and found that they only ever produced muons when they interacted with matter, never electrons. So there wasn't just one ghost, there was a family of them. Later, an even heavier cousin of the electron was found, the tau particle. And yes, it had its own neutrino too, the tau neutrino. So now we had three flavors of neutrino electron, muon, and tau. Each was a distinct particle. This was getting more complicated, but it seemed to fit into a neat pattern. The standard model of particle physics, the grand theory that describes all the known particles and forces, had a nice spot for three massless neutrinos. But the universe had another surprise in store, and this one came from the sun. The sun is a gigantic nuclear furnace. In its core, it smashes hydrogen atoms together to make helium. This process, called nuclear fusion, releases a tremendous amount of energy. It's why the sun shines. And according to our understanding of fusion, it should also produce a colossal number of neutrinos. Specifically electron neutrinos. Scientists could calculate exactly how many neutrinos the sun should be sending our way. It's a flood. The number passing through your thumbnail every second is about 65 billion. In the 1960s, a chemist named Ray Davis decided to try and count them. This was an even harder task than the Cowan-Reines experiment. The neutrinos from the sun are less energetic than those from a reactor, making them even harder to detect. As Davis built a truly unique telescope. It wasn't made of mirrors and lenses. It was a giant tank, located a mile underground in the Homestake gold mine in South Dakota. He put it deep underground to shield it from all the other cosmic particles that constantly bombard the Earth's surface. Only the ghostly neutrinos could penetrate a mile of solid rock to reach his detector. The tank was filled with 100,000 gallons of perchloroethylene, which is basically dry cleaning fluid. The chlorine atoms in the fluid had a special property. Very rarely, an electron neutrino from the sun would hit a chlorine nucleus and turn it into a radioactive argon atom. So, Davis's plan was simple, if heroic. Every few months, he would flush out the tank and use chemistry to count the handful of argon atoms that had been created. It was like trying to find a few specific grains of sand on a vast beach. He did this for decades, and he found something deeply troubling. He was only detecting about 1/3 of the neutrinos that the theory of the sun predicted. This became known as the solar neutrino problem. It was a huge mystery. What was wrong? Was our understanding of how the sun works fundamentally flawed, or was something happening to the neutrinos on their 93 million mile journey from the sun to the Earth? For nearly 30 years, physics was stuck. The solution, when it came, was bizarre and beautiful. It came from an idea that had been floating around for a while, a quantum mechanical possibility called neutrino oscillation. The idea was that neutrinos weren't just one flavor, they were a superposition of all three. Think of it like this. A neutrino is like a traveler that can't make up its mind. It leaves the sun's core as an electron neutrino, but as it flies through space, it's not just an electron neutrino. It's a mix, a quantum blur of electron, muon, and tau. Its identity is constantly shifting or oscillating between the three flavors. By the time the neutrino reaches Earth, it has a certain probability of being measured as an electron neutrino, a certain probability of being a muon neutrino, and a certain probability of being a tau neutrino. This Ray Davis's experiment was only designed to see electron neutrinos, so if 2/3 of the electron neutrinos from the sun had changed their disguise into muon and tau neutrinos during their flight, his experiment would miss them completely. That would perfectly explain his result. He was only seeing 1/3 of the total because the other 2/3 had shapeshifted. This was a wild idea, and it had a profound implication. According to the laws of quantum mechanics and relativity, for a particle to be able to oscillate like this, it must have mass. It can't be massless. The rate at which it changes flavor depends on the tiny differences in mass between the different neutrino types. So if the solar neutrino problem was real, and if oscillation was the answer, then the standard model of particle physics was wrong. The neutrinos, which the model had declared to be massless, actually had weight. The final proof came from a new generation of detectors. The most definitive was the Sudbury Neutrino Observatory SNO in Canada. Like Homestake, it was located deep underground in a mine, but instead of cleaning fluid, it used a huge sphere filled with 1,000 tons of heavy water. Heavy water contains a type of hydrogen with an extra neutron called deuterium. This made the SNO detector special. It could detect neutrinos in 3 different ways. One reaction was only sensitive to electron neutrinos, just like Davis's experiment. But the other 2 reactions were sensitive to all 3 flavors equally. The results from SNO were a triumph. When they measured just the electron neutrinos, they found the same 1/3 shortfall that Davis had. But when they used their other methods to count the total number of neutrinos of all flavors, the number matched the prediction from the sun perfectly. The neutrinos weren't missing. They were just in disguise. They had changed their identity on the way. Neutrino oscillation was real, and that meant neutrinos have mass. This was a monumental discovery. It was the first solid piece of evidence for physics beyond the standard model. The ghost, it turns out, has substance. Not much, but it's there. We still don't know the exact mass of any neutrino, but we know they are incredibly light. They are at least 500,000 times lighter than an electron, which is itself a lightweight particle, but they are not zero. Why their mass is so tiny and so different from all the other particles is now one of the biggest unsolved mysteries in science. So neutrinos are ghostly because they barely interact with matter, and they are shapeshifters, changing their identity as they travel. But where do they all come from? The sun is a major local source, but the universe is full of neutrino factories. Some of the most powerful are exploding stars or supernovae. When a massive star runs out of fuel, its core collapses under its own gravity. This triggers a cataclysmic explosion that can outshine an entire galaxy. In that brief, violent moment, about 99% of the explosion's energy is released not as light or in the blast wave, but as neutrinos. For a few seconds, a single supernova blasts out more neutrinos than all the stars in the observable universe combined. These neutrinos are messengers from the very heart of a star's death. In 1987, a star exploded in a nearby galaxy. Before astronomers saw the light from the explosion, neutrino detectors on Earth registered a sudden burst of about 24 neutrinos. It was the first time we had used neutrinos to watch a cosmic event unfold. The ghosts had brought us a telegram from a dying star. Neutrinos are also created in Earth's atmosphere when high-energy cosmic rays from deep space smash into air molecules. Air nuclear power plants, as Cowan and Reines knew, are potent sources. Even our own bodies produce them. We have a naturally occurring radioactive element in us called potassium-40. Every day, the potassium in your body undergoes beta decay and releases millions of neutrinos. You are a source of ghosts yourself. And then there are the oldest neutrinos of all. In the first second after the Big Bang, the universe was an incredibly hot, dense soup of particles. And neutrinos were everywhere, constantly interacting with everything else. But as the universe expanded and cooled, the other particles became too sluggish to interact with the neutrinos. The neutrinos decoupled from the rest of matter. They were set free to stream across the cosmos, unimpeded, forever. Today, these ancient neutrinos from the Big Bang are still all around us. They form a cosmic background, a faint hiss left over from creation, similar to the more famous cosmic microwave background radiation. There are about 300 of these primordial neutrinos in every cubic centimeter of space, everywhere in the universe. They are the oldest relics we know of, but they have lost so much energy over 13.8 billion years that they are almost impossible to detect with our current technology. They are the faintest ghosts of all. So why do we care so much about these elusive particles? Why spend billions of dollars building colossal detectors deep underground, or even under the ice at the South Pole, to catch a few of them? We care, because the ghosts carry secrets that we can't learn any other way. They are giving us a new way to look at the universe. For all of human history, our view of the cosmos has been based on light, on electromagnetic radiation. But light can be blocked. Dense clouds of cosmic dust and gas hide the centers of galaxies and the birthplaces of stars. Our neutrinos are not blocked. They fly straight through everything. A neutrino telescope doesn't see the surface of a star, it sees right into its fiery core. It can see the heart of a supernova. It can potentially see exotic and violent objects, like the supermassive black holes at the center of galaxies, in a way that light never can. Building neutrino telescopes, like the huge ice cube detector at the South Pole, which uses a cubic kilometer of pristine ice as its detector, is opening a new window on the universe. We are moving from astronomy to neutrino astronomy. We also care because neutrinos are a crack in our most fundamental theory of matter, the Standard Model. The fact that they have mass means the model is incomplete. It's a clue that there is deeper physics out there waiting to be discovered. Physicists are trying to answer big questions about them. Why is their mass so small? Is there a reason? One popular idea is the seesaw mechanism, which suggests that for every light neutrino we see, there is a corresponding incredibly heavy undiscovered neutrino. The heavier the one we can't see, the lighter the one we can. This would explain their tiny mass and point to a whole new realm of undiscovered particles. Another deep mystery is whether neutrinos are their own antiparticles. For every particle, like an electron, there's an antiparticle, a positron. They are distinct, but it's possible that neutrinos are different. They might be Majorana particles, meaning the neutrino and the antineutrino are the same thing. If this is true, it could help explain one of the biggest puzzles of all why there is so much matter in the universe and so little antimatter. According to the Big Bang theory, they should have been created in equal amounts and then annihilated each other, leaving nothing behind but light. The fact that we are here, made of matter, means something tipped the scales. The weird properties of neutrinos might be the reason. Finally, neutrinos matter for cosmology, the study of the universe as a whole. Even though each neutrino has a tiny mass, there are so many of them that their collective gravity has an effect. They are a form of hot dark matter that influence how galaxies and large-scale structures in the universe formed. To understand the cosmos, we have to understand them. The neutrino began as a desperate fiction, a ghost invented to save a law of physics. It then became a stubborn puzzle, a shapeshifter that defied our expectations. Today, it is a tool, a messenger, and a guide pointing us toward a new understanding of the universe. It is the perfect ghost particle. It is born in the most violent places, the heart of the sun, the explosion of a star, the fiery birth of the universe itself. It travels for eons across unimaginable distances. It passes straight through planets, stars, and galaxies without ever touching them. It carries with it the fundamental secrets of its origin, a message from another time and place. And, every so often, on an infinitesimally rare occasion, one of them stumbles, bumps into one of our atoms in a giant, dark detector, and tells us its story. We just have to be patient enough to listen.